everybody. Take a seat. Let's get ready to start this off. Okay. This is Paco, and he works on Arrow, and he's going to talk more about Kotlin. Nice. Give him a hand.
Nice. So the title of this talk is Simple Dependency Management in Kotlin. And the reason why this talk exists is basically because I've been working with functional programming for a while now. Me and several other people from the community were actually working on a library called Arrow that does a little bit of functional programming. And there was a little bit of a mismatch when we started looking into the way that people were learning how to do this kind of functional programming. So one of the things that came up is that there was one construct that people did not quite have available on Android up until recently. And this thing is a simple thing as interface composition. So now that the interfaces can have default implementations, you can use that to compose them together into hierarchies of elements. And that's a really simple way of doing dependency management that does not require any single framework. It doesn't require Dagger, it doesn't require Coin. It's just simply using features of the language to comport the parts that are mostly immutable, pure function. So the example for today is just me. I'm going to take a few lines of code, and I'm going to end up with the same number of lines of code, but I'm going to extract every single of the dependencies or every single of the behaviors, and I'm going to separate them as much as possible. I'm going to take it to the extreme. And I'm going to be explaining how we are composing all those elements together to form a whole application. So let's start in the IDE. Let's get used to the example that I'm going to be giving today. So we're going to define something that is an index. It's an index in a database. It's an identity. It's a user ID, however you want to call it. And then we have a user that is identified by that ID. This is our data. This is everything that exists in our domain. And now the function that we're going to be refactoring is called FetchUser. FetchUser takes an index, takes a network module, a database module, and it returns a try of user. So we have one single function with two dependencies on a network module and on a database module. And then the index, which is what we're going to use to look up the information that we need, in this case, the user. So let's get a little bit accustomed to what these different parts do. Let's start with the network module. So a network module is something that exists separate from our application. It's maybe from a library. It's maybe from existing legacy code. It's something that comes in Java. It's something that we're trying to wrap. So our network module has two functions. One of them is called fetch. Fetch is one synchronous function. That means that it gets executed immediately, that the value is returned on this same thread as soon as it is available. And what it does, it uses an integer for the ID. Sorry, it uses the index that we had before. It takes a list of headers to go to the network, and it returns you a user data transfer object, something that we are using from JavaScript. From JavaScript, from JSON, something that is like a JSON object, something that is not validated, something that can have null, something that is not necessarily on your domain. It's just a wire format. And the implementation for fetch, there's a little bit of real world in here. And real world is the way that I've used to spice the example up, which is just basically some possibility that is going to throw an exception. So we're taking a lambda that is called f, a generator, and we're going to run it, but there's only if the randomness decides that is not an exception. So this is the real world. We have something that is capable of fetching things from network synchronously or through an exception. We don't know. The second function is called FetchAsync. FetchAsync does exactly the same, but it takes two callbacks. One of them, what happens on the error case, and the other is what happens on the success case. And it returns immediately. So this means that we're going to call those callbacks whenever the information is available. We have something that is synchronous. We have something that is asynchronous. And the implementation, just for this example, is just basically calling the synchronous implementation on a try catch and calling the corresponding callback. OK, so we have our network module, we have our database module, which is fairly similar. It takes a query, and it returns a user DAO, another wire object, something that you're storing inside your database. Implementation is just some real world that it creates a user DAO, and the asynchronous version is the same. It takes 2 callbacks, and it returns immediately, and the callbacks will be called in the future. So what we're trying to do today is basically we're going to fetch from a database. We're going to convert it to a regular user from a database user. So we're doing all the validation and all the conversions that are required. And then we're going to recover, in the case that there is an error, that the element is missing, with a network call. So we're going to try to do a network call that returns a DTO. And you have to convert from the DTO to the regular one. You have to do the validation. In this example, try is a simple CO class with a success and an error case. I don't have it right now. Yeah, but it's with a success and a failure. And the constructor basically executes the function. If it's an exception, it creates a failure. If it's a regular value, it just returns that value. So that's our function. That's everything that we're trying to refactor right now. Fetch the user, network module, DAO database, and there's another part that we have to understand, which is the conversion between the user from the database and the user from the network and a regular user. And emulating some real-world transformations, some validation, some errors. There's nullables, there's all these kind of things that it can fail. So this is our whole example. This is everything end-to-end. And we're going to try to refactor into something that is going to look fairly similar, but it has a couple of changes. So it's going to be like an extension function, and instead of returning try, it's returning this weird thing. Same thing, query user, get from database, handle error with, request user, get user from the network. OK, how many people in the room so far are familiar with Arrow in general as the library for functional programming for Kotlin? We have 1, we have 2. Oh, Jesus, OK. So it's fine. We're going to start doing the version that is without Arrow. We're just going to refactor this code, the simplest version possible. So we're going to go to the framework. The first thing that we're going to do on the first step, we're going to say there's an interface that is called the network operations. The network operations is going to contain a field for the network module. And then we're going to have a function with the try of fetching elements from the network. So it returns a value wrapped in try. This is like a success or a failure value. This is a simple refactor. Basically, we have taken the same code that we had in here, and we've made it into a function. The second one is DAO operations. DAO operations takes a DAO database, and you can query the user. And potentially, on this interface, you can add all the possible methods that are available for DAO database. So for a single database, you can query the user, you can query the company, you can query addresses. The whole point is that you have moved all these functions together into one single interface, and the interface already provides the field that is required. So this is the new pattern that was not available in Java before. Instead of making everything into a class, you're making behavior into interfaces. And you can just join interfaces together to form more complex use cases. So now that we have everything that is returning a try of user of DAO and a try of query company, we probably need to take a look at the mapper. So an interface for the mapper basically says these functions that are transforming, instead of happening in a global scope, they only happen within the interface scope. So it's the same as a class. You can only call a private method within a class if it exists within it. So we're just doing a simple transformation. We have a try that comes from one side, that is a user DTO. We just flat map it. We just try with some real world, and then we return the wrapped element. We're trying to wrap this operation that can fail and create a new value. And we can do the same from the database. So now that we have the mapper, and now that we have the framework, we can just go back and see how the usage is. So the business logic. The business logic is an interface that we are composing from the other smaller interfaces. So we have DAO operations, operations with the database, network operations, operations with the network, and the domain mapper. Each one of them defines a series of extension functions that you can operate on. So query user, in this case, is going to come from the DAO operations. To user from database comes from the domain mapper. Recover with is a function from try. Request user comes from the network. To user from network comes from the mapper. So basically, you don't have a class yet, and yet you have defined all the operations that are available within your use case, within your business logic. OK, so far so good. So if you go home and you have to take something out of this talk before everything starts getting a little bit more complicated, this is what we're trying to show. You can compose interfaces now and use the functions defined within those interfaces to generate larger ones. Later, we're going to see how those interfaces can just go all the way up to your main method, to your entry point of your application. OK, so Arrow as a library tries to do abstractions that are a little bit higher than this. So we're trying to say we want to write our business logic in a way where we don't use try, we don't use option, we don't use observable, we use defer. We can use all of them. We can make it global. The same way that we can observable can take any value inside, it can have integers, it can have strings. We want to have a kind of business logic that works for all the possible containers. The way of making this work is not available in Kotlin as it is. So what we would need is something, a function, where you can just go function of f, do thing, and this will return an f of an integer. You cannot define generics on the container. This is not a feature that is available in Kotlin. This is a feature that is available in other functional programming languages. So we said, OK, can we have this in Kotlin through emulation? And we did. So what we created is kind. So whenever you see on the future example something that is kind of an f, of a generic f of an int, is actually this. But this is not language valid. This is not valid within the language. OK, so we're moving to the next step. We are going to start wrapping the elements for these values f. So the way to make this work is that your operations are going to start returning, instead of returning a try, they're going to be returning a kind of an f of a user DTO. They're going to return as if it was a wrapper of an f. The problem with this is that we don't know what f is capable of doing. F can be any wrapper. It's literally all of the wrappers. So we're going to use something that is similar to inheritance to make this work. So we could just say if f was like a number, or if f, for example, was an observable. But the problem is you cannot define that f is an observable, or these kind of things. So what you have to do instead is use interface composition to define the capabilities of these elements. And this is where Arrow, the library that we are writing, exists. We are giving you the interfaces necessary to work on these wrapper types. So the applicative interface that I'm using here has one important method. It's called just. Just is a constructor. You're just saying for a type f, there exists a constructor just that is defined, that is given to us, that is injected, that we can use to create an element synchronously, eagerly and synchronously. We can just call it, and it will be the same as fetch. So when we are in this interface composition and we call just, we can just get the values. We can just create a new value of type f. It can be any f. It's a configuration parameter. And we can do exactly the same when we're working with a database. So now we have wrapped the network in the database to work for any single wrapper that we can define a constructor for, a simple constructor. So if it was a list, the constructor would be list of. If it was observable, it would be observable.just. If it was a coroutine, it would be simply the constructor would look like async and then return the value immediately. OK, so far so good. We're able to create some things that are eager and that are available. But we have to handle errors. So before, when we were trying, we were actually wrapping everything in a function that was try catching the value. That would just go and say, hey, I don't want to go there. It just basically try catches the value. So let's just go and change our interface applicative for an applicative, a constructor that also allows for errors. So there's a new constructor where you pass an error, and it gives you a wrap type. Let's see how this looks like. We are requesting a user. We try that we can return the value immediately. We catch, and if we find an error, we actually just raise the error. So now we are wrapping all of these exceptions into this possibility of just having a regular value or an error. What happens? List can have an applicative. You can have a constructor for list for successful values. But you cannot have a constructor for list errors. So you're thinking about try. You're thinking about option. You're thinking about observable. These things have a success and a failure case. A list cannot have it. So this pattern basically can be summarized in a single helper function that is called catch. And catch in this case, the implementation is the code that I just have. It's like try, just execute the value, and if it fails, you're just going to wrap it. OK, so now we have all our operations. Our operations can handle errors. We should also do the same with the mapper. So the mapper, we're going to go one level up, and we're going to use flat map. So our mapper receives a value that is a kind of a user DTO, it's a wrapper. We flat map it. We define that there's an operation where you can just chain it, and then we just catch the new version. So it's the same operation that we had before, flat map followed by catching, but now it works for all the possible containers. So we are working at a next level of abstraction, basically. We have defined all of this to work for all the possible containers. So we have now everything in place. We have the mapper. We have wrapped the framework. We can go back to the business logic. And then our business logic is going to look exactly the same as it used to before. So there's been no changes. The only difference is that before, we didn't have an F, and now we do. So everything is parameterized to F. And instead of returning a try, we're just returning the wrapper of the user. OK, we still have another problem. The database is trying catching errors, but the operation happens immediately. I want to call my database later. I want to pass these values around, like observables, until I subscribe or until I await. I don't want the operations to be executed. So we can define another constructor, a third one. We have the first one that is just like now. We have raise error, which is now error. And we're going to have a third one that is called defer. And defer takes a function and try catches it. Tries to figure out the element. But it doesn't execute it right now. It executes it in the future. So what we're doing here is wrapping the same code that we used to have before in a constructor for defer. So this operation that used to return a kind, a wrapper, is now within a defer. It's something that is going to happen later. We didn't have to change the business logic at any of the other layers to make this whole operation lazy. And this is only something that we did by adding a dependency in monad defer. Monad defer is the one that defines this constructor. So just is defining applicative. Raise error is defining applicative error. Defer is defining monad defer. Cool. OK, so we're going to do one last step. This last step is we are wrapping right now the operations on the database and on the network that are synchronous, the first of the two possible approaches. We want to do something right now that is asynchronous. So these asynchronous operations, basically, we're going to change from the applicative error to the next element in the inheritance chain. So I have the documentation here. And basically, we have gone traversing the whole hierarchy. We have started in applicative. We have gone to applicative error. We have done a little bit of monad. We have done a little bit of monad error in the mapper. And now we just go into monad defer and async. So async is another new constructor. Defer basically took a function f that generates a value. Async takes a callback. And this callback is a function where you can pass a success There you go. So basically, it's a callback function where you just say, I have this function as a parameter that I'm going to call, and it's going to return at any point in the future. Let's look this into context, because it's a little bit difficult to understand. So we used to have an async operation. We have the callback parameter. And then we can just call the network with FetchAsync. And FetchAsync had two different callbacks, one for errors, one for success. So the only thing that we're doing is piping the callbacks. What it used to be a regular error now is as an either, is the left side of an either that goes to the callback. What it used to be a success is something that it goes on the right side, and it just goes to the callback. So basically, with this, we're capable of wrapping every single asynchronous operation that you have. If you wanted to define something, for example, that is like observable, and you can just say observable dot just one, right? You can write something like this. Observable.subscribe, oh, come on, value, subscribe, and then 1 and 2. You're saying async of a callback, and then you can just say callback it.write, and it.left. So basically, we've been able to change from one framework to another. We've been able to wrap from one framework to another. Basically, we can wrap every single asynchronous operation as long as we are using this new constructor. So far, we've gone through the whole hierarchy. We've been able to do asynchronous operations. The business logic is capable of doing asynchronous operations now. So from end to end, we can now do asynchronous operations in a different thread. We can define another constructor, the fourth one already, that is called defer, with a coroutine context that basically starts these elements in a different thread and executes them. So at this point, we have gone through just, raise error, defer, async, and there's a new one that is called defer, and it takes a context and the function that is to be executed. And this function is going to be called in that context. So, OK, that's been a lot. We have the request operations, we have the Fs, we have all the wrappers, we have the coroutine context. Let's just put everything together and see how this looks like whenever you have to call all these operations. So the usage is, if you're in a simple function, you're just saying there's this request operations asynchronous that you can just call, and you can fetch the user. And the implementation is as simple as fetching the users, because fetch user is defined here. If you're in a class, maybe you have something that is a view model, maybe you have something that is already a presenter, you can just say, we are delegating for this interface with a simple parameter that we're passing in the constructor. If you have an activity, for example, or something that you don't have the control, that you cannot add more things to the inheritance, you can just define a separate value that is an object and use the word run to access those operations. So we can just say this object with all the dependencies, run one.fetchUser, because we're using the identifier, we're just fetching the information. And once we have that information available, the reason for executing this is that we're getting a kind. We're getting a value that is wrapped. And we can just say, this is the type. We can fix that type. And once it's fixed, we actually have, come on, import it. There you go. And now what we have is a defer. So now that we have a defer, the one that is using in Kotlin as coroutines, we can just do run blocking of a.await. And this is how the whole operation will get executed. We have a wrapper for this. We have something that is simpler. We just call it unsafe run sync. And it just runs right now. OK, so this is how we are using it. How are we building the actual object? And the object is as simple as this. We have the interface that we had before, the request operation async, and then we can fulfill each one of the dependencies individually. So because this inherits from DAO database, it requires the database. Because this inherits from network, it requires the network. And because it requires a coroutine context, we just have to pass a coroutine context. So we have 3 fields to fulfill for this interface to work. All the operations already know about these fields. You haven't had to pass that to any single function. This is available through all the different layers, all the way down to the framework, through the business logic, through your view models and everything else. And the only place where you have to define them is at this top module. It's the same as in Dagger when you have your modules that are scoped to your whole activity or everything else. You have to write this, regardless of the framework that you're using. Now, there's the last parameter, and this is async. Async is the one that is going to define what our value for f is. So we want to say that this works for any possible wrapper. And I've shown you that this works as a defer value, which is from Kotlin X coroutines. If we wanted to do observables, it would be as simple as this. From defer k, to observable k. It's going to tell me I need this dependency. I import it. I need to redo this dependency, async. And now this becomes an observable. So anything that I had to do to change from using Kotlin X coroutines to using observables was just changing the definition of my dependencies. I did a simple string replace. I brought up the dependencies into the scope, but everything was already available. So far, this is the second milestone through the refactoring process. This is the way of showing how the interfaces can compose together and how you can make all of your dependencies go all the way up to your entry point, to the start of your activity, through your main, or through your view model. Whatever is the start of your logic, you can just move all of your dependencies to that point. And you can drill those dependencies all the way down without having to explicitly define them as fields, as parameters in functions, as constructor elements, nothing of that. The only thing that you need to define is interface composition. OK, so this is the last thing. I don't know how am I on time?
The break is at 3:45.
Oh, OK, plenty. OK, so the next one is these dependencies that we have are passed as fields. So we need a framework like Dagger, or we would need a coin or anything like that to be able to fetch these individual values. This is not something that is very common in functional programming. Functional programming uses types as a way of defining dependencies. This interface composition can just go all the way down to also include the dependencies that are normally fields. So I'm going to show you a little bit how do we do this normally. We have something that is called the Keep87. Keep87 is a proposal for the Kotlin language to adopt dependency injection as a feature. So make the language be capable of drilling those dependencies through your whole application. So I have this example. One member of the community, Tomas, spent 1 month writing a fork of the Kotlin compiler, modifying things so we could have this new syntax for people to have dependency injection. It's still a prototype. It is not complete. JetBrains is somewhat happy with the direction where it is going, and we have really helpful for it. So let me explain what has changed between this and any other regular code that you have. The only difference is this with keyword. So I'm going to define a function that is capable of summing 2 elements together. Any 2 elements. It's a generic. And then we're defining an interface that explains how to combine them. The same way that we have an interface that defines how to create a constructor, we can have one that defines comparison. Instead of passing this as a value, there can be an implementation that the compiler can resolve based on the value of A for all your call sites. The same way that when you're inlining, it can reify the types, it can find the classes, the compiler can find the implementation for semigroup for the key A. And we just combine the 2 elements together, and it returns an A. Let's take a look. This function is called plus. So we have something that is called plus of money and money. Money is 50, money is 100. I execute this. It's been fast so far. And it tells me that the amount of money is 150. I have only passed 2 parameters to this function. The 3rd parameter is missing. We have not defined it. We have another call that is called duplicate. It just does plus of an element to himself. Same case. It just has a dependency on a semigroup that exists at the global level that is injected directly. So you can call duplicate on money, and it will find it. The compiler will be able to inject this value for you. So let's run it again. 43, 86. OK, but how does the compiler find this element? We have to go to the second part of the additions to the language. So the second addition is the keyword extension. You have a data class, you have an inline class, you have a seal class, and now you have an extension class. And an extension class defines the global implementation of these interfaces for your whole application. So the compiler can just go through your whole program, find all the definitions of extension, and then put them in a dictionary, put it in a global map from type class, from interface to a specific type. So in this case, we have the extension class money semigroup. The name is irrelevant, which is for a semigroup for a combination of money. And the combination of money, because money is just a double amount, it just adds the money together. If I just want this to be a multiplication, it will just run. And then instead of summing, they are multiplying it. It's a global instance. There's no state. Because there's no state, because there's no mutability, because everything is pure, you can have a global instance, and nothing will modify it. There will be no errors. There will be no problem. This is the way where functional programming languages do dependency injection. because everything is pure, because everything is immutable, you can have definitions at a global scope, and they are safe. And you can inject those through the whole application simply by using the compiler, if the compiler understands what they are trying to look for. And that's what the keep87 is. It's a way of defining how me as a client can ask for a dependency and how the system can just look for it. So if I just went and I did, OK, I want, instead of summing money, I actually want to sum two numbers, 1 and 2. I compile this, and it tells me, it's really small, but it basically says, unable to resolve implicit parameter semigroup. It says, I couldn't find an instance of semigroup in the whole program. I ran through everything, I couldn't find it. This is exactly the same thing that Dagger does. It finds everything. It goes through the whole program, finds all the dependencies, finds all the keys, all the elements, puts them together in a huge global map, and then they just put them in the places where they are required. Or it does some code generation. It does many more things. It's really good. But we're trying to put this on a language level. And the good part is this also works for the wrapper types. So we can define a function increment that works on any wrapper that wraps numbers, and it just adds 1 to them. Or we can define a cross product of 2 elements. And I'm going to say, OK, I'm going to increment a list, or I'm going to do the cross product of 2 lists. I can run this, and boom. If I put a 10 in here, or I put like a 300 in here, or maybe I change the operation from plus to sum, it doesn't really matter. I can modify both sides of the elements, and it's still going to be working the same. OK, so with this information, understanding this, how do we go back to the original code that we're using and transform those field dependencies into type dependencies? OK, let me close all of this. So let's go to the advanced version of the framework. Same as always, we're going to define an interface that is called a network fetcher. And the network fetcher has a generic. This generic, as you can see, is not used anywhere because it's not relevant. But this N is the key that the compiler or Dagger or any dependency injection framework is going to use to find your global description. So we can define a network fetcher with the synchronous operation, with the asynchronous operation. We can define all of this. And now we have to provide an implementation. And I'm going to provide one implementation for a global network operation. So the same way that we used to have request users that depended on a field, and the field was the network, now we depend on the network fetcher of N. We can just call the same operations. We can call FetchAsync. It's the same thing that it used to be before. The only difference is that now, instead of being a concrete field, I think this is going to be easier if I just go back to the other framework. Yeah. So instead of calling for the network module, it's actually calling whatever the implementation of the DAO fetcher, of the network fetcher is. So again, we have gained another layer of genericity. Now we have 2 parameters instead of 1. If we go to the business logic, this one. The business logic now composes with 3 keys. It used to be 1. It used to be simply request operation async of f. Now it's based on f of an n and a d. And we still have the same asynchronous of f. We have moved coroutine context from being a field to being a parameter. DAO operations async. Network operations async. And the domain mapper doesn't depend on anything else. So you have defined all the possible dependencies, f, n, d, and the coroutine context. Everything as a type. Ones are generic, ones are particular. And if you go to the usage, to the new version of the usage, there you go. So this is the old version. Let's do a side-by-side comparison. The only difference between one and the other is the 2 new keys. There's nothing else. Everything else is exactly the same. Now we just depend on 3 keys instead of 1. And when you're doing the definition of your object, everything, instead of being in a field, as it was in here, everything is a type. Everything is a global value. We have network module.network fetcher, DAO database.DAO fetcher, coroutine context, dispatcher's default. Implementation is empty. Everything has become a type. And we know that the compilers are capable of resolving these types because we can give them hints. So the version that Arrow provides today, the one that we're giving until keep 87 is complete, is based on annotation processing. So what we do is we put extension, instead of being a keyword, now it's an annotation, and instead of being over a class, it's over an interface. But basically, when you define an extension interface, in this case, we delegate to like a global network module, we generate this extension function on the companion. You can find all the type classes defined for that specific type in the companion. So we can define both the network module one, which is delegate, the FetchAsync one, which is delegate, and it's the same for the DAO database. And we can have this global access to them where you can just put them as a type, so you can just take them anywhere. So now you can put everything together. It just works. OK, so that's pretty much everything that I had to explain today, if I remember correctly. I have one more thing, but I think it's better if I skip it. So that's the main idea behind the whole functional programming, dependency management, and everything else. You can just get away with a lot simply by composing interfaces. And you can get more level of configuration if you move parameters to types. And in the future, those types are going to be able to be resolved by the compiler. This is a reality that is happening. Type classes is something that even JetBrains has expressed interest in. That's what type classes are, basically. Those interfaces with the generic keys that you can look up. OK, so if you want to know a little bit more, we have the documentation with all the type classes, all the generic behaviors that you can use to compose your more complex operations, to compose your going into the network, going into the database, getting these things together. All the constructors, they're all in the Arrow library. The Arrow library defines show, which is converted into a string, equality, orders, combinations, constructors. We have all these many things. That is the same tooling that people in functional languages use. We have people coming from Scala. We have people coming from Haskell. When they just go, OK, where are my regular tools? Here they are. They have been using this to compose their elements. This is how they're using their dependencies. Cool. So this is my last slide. This is a little bit of takeaways for home. If you want to take another look at this example end-to-end, it's uploaded already to the Arrow repository as an example. You can find it in the first link. On the second link, the first link is actually a blog series that I wrote that basically summarizes these concepts. And the rest is just follow-up of how can you use these type classes, how do you write a program end-to-end using all these generic parameters. All of this composed together, more or less, to form the content of the talk that I've given you today. So yeah, my name is Paco. My website is PacoWorks, @PacoWorks, or PacoIto in GitHub. And these slides are already available, so you can just go on the link. Thank you much.
Wow, thank you, Paco.
Yeah.
We have a few minutes for some questions, so if anybody has any.
So who is using that in prod? Do you know?
Well, I wrote about this not so long ago. So we're using this in Arrow as the library. This is how we define the composition. So I will guess 47 Degrees, the company that is using this for product development, are the ones using it. So we're doing the promotion right now. We're trying to explain people these ideas. And until Keep 87 is here, it's going to be a little bit complicated to get it end-to-end.
Hi. First of all, thanks for the great talk. I was wondering, because you mentioned annotation processors and this implies generation of code, how does this hit the build time?
The what, sorry?
The build time of the application.
I mean, Arrow is, the generation that we're doing is not too complicated because we don't have to traverse anything. All the information is already available. So the code generation is mostly boilerplate. Not very slow.
Yeah, but I mean, the more you use it, the more classes will need to be generated and the more build time will be used.
Yeah, that's an obvious one.
Because when you mentioned Dagger, we're using Dagger exactly, and I've seen all the classes that are generated based on annotation processing, and it really bugs me that it's like it can take up to a minute just to generate everything.
So you're defining one element for each global, for each definition, but the point is the only type class that you need to generate is the one that you're injecting. So you only need a handful of them through your whole application to make it work. You can compose them together as simple values, but you don't have to make everything into an extension interface, basically. So we only need, in this case, we only needed the database and, what's the other one? The database and the network. That's two. We already have the generation for the rest of the generate components on Arrow, and there's very little else. If you have more things through your application, more business logic, the business logic you're not generating, right? Which is the case when you're using Dagger. Dagger generates everything because he has to go through all the classes, all the constructors, and everything else. Whereas for us, we only create things that are existing at a global scope. So we don't need to traverse the whole program. We only need to generate a small amount of code based on the information that we have. So it's faster than Dagger. Obviously, it's faster than Dagger. It is slower than not doing it at all. I cannot give you the numbers because I don't have like an example end-to-end for a large application.
Okay, cool. Thank you.
Cheers.
Again, give it up for Paco. Great talk.
Thank you.